with actually how many years? Okay, 13 plus 15.
Okay. Okay. Thanks all. And hopefully, as told Pat, it should be hopefully not too painful, maybe even educational. We'll see what happens. This is very much the spirit of a Friday morning at the festival, kind of a bit of a just-in-time thing, but hopefully I've pulled together something interesting. Let me start by thanking various collaborators I have listed here, who've all definitely given me a lot of help, but this is something where by and large I've gone off on my own, so it's definitely a credit to them. Yell at me when I say something offensive and dumb, so don't blame them. And the idea here is to look at basically starting from a separate project. I'm not trying to minimize how much I talk about looking at compact reactors. Just kind of generally what things can we learn about turbulence and transport in a Tokamak power plant? What are almost kind of the more general things that have to happen there? So, for the students, two things I always like to remember here. All models are wrong. Some of them will be useful, I think, in the spirit of our reduced models here. Of course, I think something that will resonate here. Nobody believes your simulation unless you did it, and everyone will believe the experiment unless you did it. And there's apparently a more ancient one that you can ascribe to Albert Einstein, where you can replace simulation with theory as well. So you don't have to do numerical simulations to be disbelieved. But especially for today, I think wrong but useful is an important thing to keep in mind, because you can have a perfectly valid and elegant model, and if it doesn't ever apply or let you take any actions, it may not get you much more than a paper. So figure out what you want to do with the model. So the background of this was a project I had started recently, developing compact reactor scenarios, more with the idea of testing the predictive models and then coming up with, okay, this is what the scenario will be. This is motivated. There's been a lot of private and public interest in the US lately in developing more compact fusion power plants, just because of advances in magnet technology, looking at how the energy markets change, et cetera, et cetera. The UK as well is also doing this with their STEP program. And so this almost more for my edification, but hopefully for others as well, in the interest of trying to figure out, well, how confident should we be that we can go towards this new regime that we haven't really thought about in a while? I wanted to use our various integrated modeling tools to scope out what some potential compact reactor scenarios might look like, more with the intention of seeing, how close are the parameters, the dimensionless parameters, the operating conditions in those scenarios could be to what we have now, and use them to benchmark, our reduced model versus more advanced models for some nominal parameters, rather than saying, this is definitively what a compact thing is. Like, okay, this is what we think it might look like. Does that actually line up with where we are now? So that's very much the spirit here of these things. So, there's a whole power plant design, conceptual, drawing, and then just sort of, kind of go up on working out, can you just get 2D equilibrium? And this is very much still something in progress, but I think it's already provided me some useful insights and some things that hopefully may be useful here as well. And so just kind of the kicker at the end of the day, what I'm going to hopefully maybe try to convince you, and I'll say this deliberately, provocatively, in a way that gets people maybe thinking and figure out how do we shoot down this argument. But what I'm going to claim is that if we look at these burning plasma scenarios, so plasmas that are dominantly self-heated rather than externally heated, you can identify some core transport and turbulence properties that any viable, in the sense of consistent with engineering and economic constraints, is going to have to exhibit. And this is going to be true whether or not you're looking at either an inductive or a steady state plasma. But basically what I'm going to say is it's going to have dominant electron heating because it's a burning plasma, but it's going to have to be well coupled enough that a bunch of that heat gets into the ions. And at the same time, because of the temperature and stuff you have to be essentially a relatively collisionless plasma. So at the same time, you have to have this collisional exchange transferring energy, but you have to be confining the energy well enough to keep that energy in the ions. And that means you're going to have a fair amount of transport through the ion channel. And if you look at the physics of the various micro instabilities, various processes that can transport energy through your system, that has very specific implications on what modes can really dominate transport, because as Carlos was talking about yesterday, the cross phases between different fluctuations, that's what sets the transport. Those cross phases are quite sensitive functions of what instability is acting. And there's only certain instabilities that are going to be consistent with sort of that transport picture at a high level. And particularly what this means is that essentially the transport of all of your channels is going to have to be driven by long wavelength ion gyroscale transport. I'm not saying all the transport, but that's going to have to be a major player basically in any kind of viable reactor. At least that's the contention. And so, just showing up here, kind of our standard metrics, which is for a working fusion reactor, we're with this triple product, density, temperature, and confinement time up to some high value, and we have to use at a certain temperature. But there's other metrics you can look at, and so this kind of picture, two things you can think about. One is what I'm calling a coupling metric, the ratio of the energy confinement time to the time the scale takes to equilibrate the plasma, the energy between them, and then also the ratio of the ion to electron thermal diffusivities as a fingerprint for what kind of transport you have. So just as an outline, and I'm sure I'm already going far too slowly, try to talk just very quickly about how we do predictions of core reactor transport and confinement using some reduced models. Then go into a simple model of reactor power flow, basically just kind of what I went through and the transport requirements. And then at the end, time permitting, I'll go into some of the aspects of where does that leave us in terms of what the models say now, what are the open questions, what needs further investigation. So of course, if we want to actually design a whole fusion reactor model, there's all kinds of different processes going on here, just sort of a schematic of all the different things that can be integrated. As a tremendous number of time and space scales, and something like a whole climate model. Like you have just not just the ocean, but you have the wind, you have the earth, you have everything, heating, and so on. And so to pull that all together is practically impossible in some sort of one integrated model of everything. So the idea is one way or another, you have to couple reduced models, different sub-physics models. This is something very out of date, just kind of illustrating how many different codes and models there are that you could pick and choose from to maybe bring together into some integrated simulation of all that. And so I'm going to try to focus on a much more simple problem of, just focusing on the core, transporting the core, assuming we're macroscopically stable. I'm not worrying about a whole bunch of stuff. So just what does transport in the core of our plasma look like? Sometimes we'll call this 1.5D transport modeling. And the idea there is if we have an axisymmetric system, our magnetic equilibrium is going to stable. It's going to be inherently a set of 2D contours of these nested flux surfaces. That's determined by the Bragg-Shafanov equation there. So this relates how your magnetic flux psi in actual configuration space relates to the pressure in this parameter F that's essentially a function of the current. And then the plasma rapidly equilibrating along those flux surfaces is what makes essentially the P and the F just essentially one-dimensional profiles. And so that's, we can take this whole 3D system down to a 1D transport prediction ideally. And so already you can kind of see this is sort of already getting to this model reduction. We're going from the full 3D time to getting down to what is the kind of slow, confined evolution of this average macroscopic profiles on macroscopic timescales. Just kind of showing there what the pressure and the current density may look like in full D3D experiments. So D3D is a Tokamak in San Diego, sort of a standard operating machine right now. So obviously we have those transport equations. Once you do this averaging, you can write in a standard conservative form. Evolution is divergence of a flux and some sources. Very often the d by dt terms on the left, when you're seeing this transport timescale, are actually relatively small relative to those other two terms. So you might actually kind of move them over to the right-hand side and think of your, what we call like a W dot term, how fast your density or energy is changing. It's like that's another source or sink in your rather than the sort of leading order thing. And the other thing I want to kind of emphasize, it's obvious, but it has some implications later on. Often we'll talk about flows instead of fluxes. So that's just integrating the flux through the surface. So what's the total amount of energy through a surface? But whether you're talking about flows or fluxes of energy, particles, momentum, the key thing is that's just the integral of whatever sources are inside that surface. And so that's very often what we call the experimental fluxes, is some independent calculation of your heating and your radiation, all that stuff I'll talk about in a second, and what that integrated flow is. But when we think about things like, you may have cases where you may have like effectively like net zero net particle flow because you don't have any sources inside. That doesn't necessarily mean you have no transport inside or nothing. You can have fluxes and things pulling things in. But when I talk about flows, that just means I've just done a volume integral of the amount of that source or sources inside a surface to kind of present things. Yeah, I think we've kind of gone through this. We all have heard lots about turbulent transport, but just at the basic level, there's for something like the transport equations, we have two essential mechanisms that provide transport. What we call a neoclassical transport, that's just due to the collision process. So that's just kind of standard collisional heat and diffusivity. There's modifications for the geometry and so on, but it's fundamentally what it is. In current devices, this is usually, not always, pretty negligible, except very near the axis or in certain conditions like a transport barrier at the edge or so on. The key point here is that, however, that diffusion coefficient, or that your diffusivity, is going to be proportional to the ion-ion collision rate. And so when you go to a reactor, that process is going to get even smaller, just because you have to get even hotter than we are now. Even if you get a bit more dense, you get even bigger and hotter. So neoclassical becomes essentially negligible throughout the entire reactor, just because of the conditions you have to be at. And so what one implication already is for systems now where maybe we have regimes that have significant neoclassical transport, those almost inherently cannot scale and be the same in a reactor, because if your neoclassical transport is big enough relative to the turbulence for it to matter, it's very hard to imagine how you've gotten into a self-consistent state that's at the temperatures to be generating that fusion power. So that's the kind of statement I want people to think about. It's like, when and how could you maybe break that statement? Because I'm sort of asserting it at a hand waving level, but it's easier said than done to actually break it and keep everything else pulled together. Now, of course, in addition to the neoclassical process, we have a turbulent process. We develop various instabilities driven by just inherent radial gradients, free energy equilibrium profiles. And what I do want to note is both of those processes can drive both inward and outward particle fluxes. So different instabilities can actually suck particles in as they move energy out. Neoclassical processes can sometimes pull in impurity ions, even if they push out the Bain ions, your working gas, and vice versa. So that can be something where you have zero net particle flux, but you may have different transport, different wavelengths, different species moving in and out. And so that's just part of the fun of modeling the plasma. Just on the other side of that equation, there's lots of different sources and sinks in a fusion reactor. And let me see if I can move stuff around. So what I'm showing here now is an example of these flows. So on the left is this is a calculation for either baseline scenario. On the left is what's the various essentially volume integrated sources for the electron energy channel and the ions on the right. And just kind of going through, here in green is essentially the auxiliary heating we're putting into it. So the neutral beams, the RF sources we're using to heat the electrons. Oh, yeah. So probably that's better. Other way, yes. Okay. So here, this would be our auxiliary heating. This big high line here is actually the alpha heating. So as you generate fusion reactions, you generate these energetic alpha particles. They collide with the ions and electrons and transfer the energy. Functionally, at reactor relevant temperatures, that ratio is going to be 2 to 1. So about 2/3 of the energy generated in a fusion reaction is going to be transferred into the electrons. 1/3 is going to go into the ion. And this is where essentially the idea of having dominant electron transport comes from. If you're producing power, you have to be dominated by the fusion reactions as opposed to the external sources. Otherwise, you're not generating so much heat. You're not generating enough heat to make net electricity. And so if you're dominated by that process is dominantly heating the electrons. That just puts you into that state. Now, of course, the balance to that is the various loss terms. So the electrons will be cooled off by different radiation sources. So there's Bremsstrahlung, synchrotron radiation, line radiation from different purities. And so those are these kind of little lines up here. You can see, say synchrotron rate velocity pretty small, Bremsstrahlung, and line radiation are equivalent. And then here in red, this is that collisional exchange from the electrons to the ions. So most of your heating is going to the electrons. The electrons get hotter than the ions, and then the nature of the collisional exchange just takes some of that energy out of the electrons and puts it into the ions. So if I look over here for the ions, the total essentially energy flowing through the ions, some of it's coming from fusion power. You actually get an equivalent amount of heating to the ions just from that collisional exchange. I have a very minimal amount of external heating. And then here in blue is something we don't actually include right now, but you in principle can in these models, which is a turbulent exchange. So when I talk about exchange right now, that's just purely the collisional classical exchange of ions and electrons combined. But different, there's at least some work that says different turbulence instabilities can also facilitate a transfer of energy between the ions and electrons. That's another source you could put in if you have a model of that you trust. In the one we use, we have the prediction, but we've never really validated use it, and it's also, at least for these predictions, relatively small, so we don't include it. But that's kind of an example of where there's an opportunity for more reduced modeling to come into this kind of picture. Yeah, this is a prediction for the 15 megaamp heater baseline scenario. It's about U of 9 point something, so it's kind of sort of that. Okay, so now when we do our actual transport modeling, the technique we use is essentially something more like a control volume or finite element, and then basically transform essentially the steady state transport equations into a nonlinear finding problem. The fundamental assumption is that, again, on this macroscopic time scale of interest, everything's kind of slowly, smoothly varying function of the radius. And so what we'll do is we'll parameterize the density, temperature profiles in terms of piecewise linear scale lengths. We call it G here. So say for a temperature that's, say your minor radius over temperature times PDR. And we'll just do this on a relatively coarse grid. And then, once you have this and you have a boundary condition, so say my temperature out at some radius is just, I help hold that fixed, I can always integrate this Z profile to get the actual temperature. And the reason we do it this way is we think in terms of the physics understanding we have that these normalized gradients, those are what actually controls the actual dominant sensitivity, let's say, of the turbulence. If the turbulence is often quite stiff with respect to that gradient, so we're going to use that as our kind of iterating parameter, but then you can always take that back to the actual calculation. And so then just in the language of what we've done before, we can formulate the transport equations as a root finding thing. Basically, you have your neoclassical flux, that's a function of the gradients, turbulent flux is a function of those, and also all the other parameters I'm not writing here. And then nominally those should balance that, what I call that experimental flux, so the integral of all those different source terms on the right-hand side, but those are also functions, say, of temperature. So if I just rearrange that, then I have these two things should equal 0, and I can take all my favorite root finding algorithms for multidimensional things and iterate with that, given models of the turbulence and neoclassical transport. Yep. Yeah. Mm-hmm. Yep. You can, yeah, I mean, in principle, right, there's nothing that a priori requires you to fix the boundary. I mean, in principle, yeah, we've had times like you could put that to what we call like that pivot point where you constrain the actual value. That could be anywhere in the region you're choosing. Part of where we've gone is try to say is, one of the things is, okay, how far out in radius am I going to choose to do this integration? And then how do I want to connect that to this edge transition region and then out to the scrape off layer? So, if I'm modeling a current day experiment where I have actual profiles and things, then I can take that pivot point, say, from the experiment or try to reproduce it. When we do actual projections for future things, one of the things I'll show a little bit is you can take like a prediction from, say, EPET or some model of the edge region, and then say, okay, my out at say row up to row 0.9 comes from some other model. I use this approach out to say row 0.8 or 0.9, and then I may just literally connect them, and then I iterate between these different models until the whole thing is self-consistent solution. But yeah, it's there's nothing that requires you to be fixed there per se. Yeah, I mean that's in some sense this is part of the assumption now. I get this, and so this is sort of where it comes down to the all models are wrong, but some are useful. I think yes, I'll try to show that this approach can reproduce the actual kind of profile, say measured average over tens 20 millisecond kind of thing. So yeah, I would if I was trying to capture the very fast turbulent timescale dynamics at a fine scale, then this is not the way to do it. If what I want to know is roughly how much pressure is my thing going to have, I can tell the engineers, this becomes more sufficient, as long as things have not stayed stable enough. So for ITER, I mean, I call the Q experiment there. I don't like actually calling that the experiment, because it's a separate set of calculators. Like those fluxes are never measured. What that comes from is actually, I'm going to call my new beam or my different sources that calculate, okay, how much auxiliary heating and stuff, and how is it being absorbed. So for ITER, I say, okay, this ITER scenario has this many neutral beams aiming at this target plasma. And you do a calculation for, okay, this is what the sources and sinks are from that beam given, from those RF generators. I can calculate. Yeah, so yes, so and that's why this essentially that Q experiment, those sources actually also depend on Z. That when we do this transfer, so that you can calculate, okay, in my model I have some given iteration, I have some density, some temperature. I can calculate the radiation losses. I can calculate diffusion. Given those, and that becomes part of your iteration as I'm iterating those internal sources, exchange, diffusion along with it. And then normally what we'll normally do is hold the auxiliary sources constant, but you can in principle update those as well. So if you thought, okay, my deposition from the neutral beams of RF efficiency or something is going to really change as the temperature change, you can in principle update that as well as you find your solution. Right, so maybe this towards some of the questions. So this is an example for a typical D3H plasma. Profiles average over a couple 100 milliseconds. But, the dashed lines here are fits the actual experimental data, and then the red lines here are predictions using this approach of, okay, I'm going to specify out to row 0.8, the outer 80%. Does my calculation of these sources and all, how well does that reproduce the interior? And so, it's obviously it's not perfect, there's some peaking right here, but in an overall sense, depending on what you need to get out, that may be good enough if I wanted to say design the experiment. Yep. Yeah. So yeah. So which flux didn't work? Yeah. Yeah. I mean, there's different things. I mean, sometimes you can have, I mean, in some sense, we by design pick solutions where, say, you're not right at the edges, say, disruption or tearing, so where things are really evolving rapidly. But if you're evolving slowly, then it's quite small. I mean, yeah, there's some wiggle, but within probably the uncertainties of the data, you can't do it. Sometimes, often, they'll actually run the like the beams and sources actually in feedback, and so you can actually keep the plasma pretty much steady for multiple seconds if you do that. So, again, that's something, if you want to capture it, you can do something more advanced, but if that's not your goal, then you don't know. Yep. Some of, I mean, I would not in like, I have some, I mean, I could guess a couple different things. I mean, some of like that's a measure of how good the models are or aren't. And I'll talk about a couple of assumptions, but in some sense, I'd say if nothing else, we're assuming so local transport there, and whatever we want to argue about, like sort of the middle and out, like once you get into 10-20% near the axis, one eddy covers probably out to 0.2 there. So I'm not surprised if you're not exactly right. I don't think, at least at the time we're looking at, I'd have to go back. There may be later on, but I don't, not there. Yeah. Not, at least right now, I think in this one, I'd have to go back and wait. This is just my dugout from a while ago. Okay. Yep. Yep. Yeah. Yeah. Exactly. Please.
I mean, it strikes me, you're talking about it, one of the interspecies transfer, what's in the model for collision discovery?
In like the turbulent exchange?
Yeah.
So that was this, there is in principle in TGL, the model we use. Right. I mean, it does make a prediction for a turbulent exchange. Right. But frankly, we never use it just because I don't think any of us really believe it, just because it's never really been tested or validated. Right.
But it becomes, I think, very relevant.
Absolutely. Yeah. So to the extent we have a model and a calculation, it predicts it's this blue thing, which would be a correction on that red one. So the prediction is it's small, but that's a prediction of a model we have no real confidence in. So
you're effectively.
Yes. But knowingly ignoring it, not unintentionally. Yeah. Yeah. Yeah, it's, I mean, I'd have to, there's, I mean, Pat and the student wrote some, and then there's a paper that Gary wrote. Yeah. Okay. Right. Okay. Well, I think maybe we've gone through, but here's a list of heretical assumptions or unorthodox, depending on which part of the ocean I'm on. But basically, what we are assuming here is that the neoclassical and the turbulent fluxes are indeed separable, independent, and local. Now, I can be burned at the stake or martyred or whatever, depending on where we are. I would say that the way that the argument for this comes from essentially, you can do a very systematic, rigorous derivation of transport equations, starting from Tokamak, using the Rostar extension, blah, blah, blah. There's a really nice set of papers by Sagama et al. And also Enable that kind of lay out, okay, if you take this approach, here's a set of equations that gives you something. There's also just a practical justification that this is something that seems to work well enough now, whether or not we should trust it. As far as calculating the neoclassical transport, you can use any variety of different things. There's analytic models, more semi-analytic ones, direct solution of drift kinetic equation. That kind of, that's, any of those are able to be done fast enough that they're not really a rate limiting, kind of resource limiting part of the modeling. That's really comes from the transport. And practically, what we use is analytical, semi-analytical, or most frequently quasi-linear models for the turbulence. And this is just because even in a case like what I just showed, you have to, even if you're doing this evaluation only at 7, 8 points, if you're doing multiple channels, you're trying to get convergence, you have to calculate Jacobians and things. Finding that root finding requires hundreds of evaluations of the flux. And if you try to do nonlinear turbulence simulations, well, even if it's just one, it's just it's thousands, tens of thousands of CPU hours. You can't kind of go through this quickly. And that's, in some sense, like that's not the point of this model. The goal of these models is to something that you can iterate on that's good enough, not be the exact perfect solution. I mean, ideally, you always want to get better, but that's not necessarily, you're knowingly trading off some potential accuracy for speed and convergence in order to say it's scope through different scenario development choices. However, there is a fair amount of increasing use of machine learning and neural nets to speed up performance. I'll show an example of that in a second. Of course, probably part of the problem is that if you want to do that, there's quite a range of potentially relevant transport driving instabilities on a whole different range of scales. So in Tokamak's 3 very common ones we have that exist at different wavelengths. At the longest wavelengths is called the micro-carrying modes. This is something that's driven by the current gradients and collisionality, temperature gradients. For our popular one is the ion temperature gradient mode. So just inherently you have an ion temperature gradient. The system wants to relax that free energy to move the ions around. And then if you get down to smaller scales, you get the ETD, so it's the electron temperature gradient mode. So this is something where even in addition to whatever is going on those ion gyro scales, at even smaller, finer scales, the electrons can still do their own moving around thermal transport. So this is just kind of an example from a simulation we did in PPV a couple of years ago, just kind of showing the coexistence of all those different scales of turbulence in a heater baseline scenario that had both ion and electron heating. Sort of for reference, this is 2 centimeters in the machine, so you just kind of get a sense of what range of things can be going on. So as a kind of reference sometimes, we use what we call the quasi-linear TGLF model for this work. And I apologize, this is something I probably should have, I don't know if I should have, or we just skipped over this, but the details of what this is, I'll just try to go through quickly, maybe easier for me to explain later if needed. The TGLF, which stands for Trap Gyro Landau Fluid Model, is a quasi-linear transport model, and what it does is it solves it's a combination of analytic approach and calibration to nonlinear simulations. It doesn't have any calibration to experimental data. So the basic idea is that at least in the core, we're in this kind of small row star expansion, the fluctuation is relatively small. A lot of the linear characteristics are preserved. And so you take a high set of moments of the kinetic equation and linearize those, and you can solve then this sort of things like an expanded version of the Navier-Stokes equation to get the phase relations between, say, the potential and the density, the temperatures, and so on for different scales in that limit. And how accurate that model is comes down to how many basis functions you want to use, how many moments you want to keep, et cetera, et cetera. And that gives you then the idea is, okay, that's going to tell me what's the cross phase and such between say the temperature and the velocity fluctuation that Carlos was talking about. But I still need to know what's the actual absolute amplitude of those fluctuations, make a prediction of the flux. And so that is what we call the saturation rule. And this is sort of what, I don't know if you'll call it semi-analytic or what you want to call it, but basically it has a model form where sort of the general structure of that form comes from theoretical understanding. So it's generally the growth rate to some power divided by wavelength to some other power. So something like a mixing length, but there's lots of generalizations in it. But then the actual exponents, say, on the growth rate and the wavelengths and so on, are free parameters. And those then get determined by calibrating them to a big database of nonlinear simulations that scan different parameters. So the idea is you get the details of that saturation from calibrating to nonlinear simulations, but then you kind of boost that finite number of nonlinear simulations you have with this fast ability to calculate the cross phase for any specific exact parameters. And then you can show, at least when you go to this kind of training database, which is only 80 simulations or something, it's not enormous, that you actually do a pretty reasonable job of at least capturing the energy fluxes, a little bit less the particle, but this gives you a reasonable approximation in core seconds to a core minute rather than tens of thousands of core hours. So that's just the trade-off that you're making. So just kind of another example of how this would work that maybe kind of goes at the boundary value question. So this is now another prediction of a different, maybe the same, a different thing. You can see now we made a prediction across the entire profile, like we're not stopping just on the axis. And what we've done here is in this internal region, we use this quasi-linear transport model I just talked about. But in the outer 10%, we have another model that is aimed to describe the pressure and the transport in that region. And then so you make a prediction for the outside, you make a prediction on the inside, and then basically you just do like a linear interpolation of scalings between them. And so it's not great, but frankly, if I stop here to here, it's actually a small enough region of the actual plasma that even if I'm not quite right, you can't kind of go too far awry. And so if you then iterate between those predictions, you can get something that predicts the whole profile without, say, needing to know what was the density and the temperature at the top of that radius. And that's the approach that you can then take for predicting a future device. Like either. That is up to the user to decide. I mean, that's sort of not a great thing there. I mean, functionally, what we'll do is kind of say stop. In the cases I'll show, like I might stop for the reactor. I might stop out at rho 0.9, and then have that be kind of contiguous with a solution I'm getting that comes in. But yeah, I would say in that kind of this kind of somewhere between 80 to 90% is just empirically where it goes, and that's to some extent from okay, this is out to about the region where we get the TGLF model seems to work well. Like when if you go beyond that, you're getting into things like ELMs and stuff that's not in the model, or using like L nodes, you can maybe start going out further with the higher saturation with the you can do that about still in. What'll happen is, like if I stop, say out here at say rho 0.8, and I have the other, like at that point, like I just I just match the fluxes to that radius, and then I just have some other profile. And I have some kind of jump, and what that'll give you is some like, if it's not all consistent, what'll happen is you'll get like some very obligate profile, like my core has like some big kind of perturbation up and down, and then if I feed that back into my initial calculation, that won't be consistent. Like I've changed now the global beta that determines what's out at the edge, so then like that'll update. So the two of them actually iterate back and forth together to come to a solution. And the test of the prediction is where those two iterate together to, and that lines up with the data. I can't even imagine where I am on time at this point. It's probably will be honest. Okay. So just as an example of how you can start speeding stuff and actually start going to bring in more exact models, there's been some really interesting recent work by Pablo Rodriguez Fernandez and Nathan Howard at MIT, where they couple a sort of a similar approach here, this kind of iterative transport model. They're actually now using nonlinear gyrokinetic simulations just at a few radii. And essentially to speed things up, what they do is, I can't really do it justice, but I refer you to the paper. Nathan will have an invite to talk on this as well at APS this year. But basically, use this kind of Bayesian optimization framework. So as you start doing the iterations early on, you have to do a bunch of calculations, but if you cast it in the right dimensionless parameters, you kind of build up a sense of, okay, this is what's mattering, this is what isn't, and you can use that to essentially optimize how fast you go to a solution rather than not kind of learning from previous iterations. If you imagine doing like a standard root finding thing, you might have found out like, okay, I got this set of values as I scan this or that parameter, calculate my Jacobian, and then you kind of forget about that for the next iteration. But if you keep track of all that, you build up this database, you can essentially speed up how fast you converge to things. So that's my best understanding of it. I encourage you to go see them. But again, it's sort of the proof is in the pudding here. This is a prediction for another D3D sort of eager baseline experiment where here's the actual measured data involved with blue points, predictions for the profiles in red. And one interesting thing here that we've been able to do is predict not just the electron density, but also the amount of carbon, so the impurity coming in. This is a particularly important thing for either in future reactors where you're worried about how that's going to play out. Okay. So now just maybe hopefully getting into some of the actual stuff. So kind of, okay, I have this tool now. I want to go apply it to actual reactors. Like, what is a compact reactor going to look like? And so the basic question I pose is, what would a reactor that's capable of producing 200 megawatts or more net electric power look like at a size that was substantially smaller than EAR? I assume I can take advantage of this new generation of high temperature superconductors, go to a higher field. What would a DT Tokamak standard positive triangularity H node and so on? And so just kind of come up with all the boundary conditions about the shape and the size and so on. I basically followed this approach laid out in this tutorial paper by Jeff Freiberg, which I think may be my favorite paper of the last 10 years. So anyone out there, especially younger students, if you're interested in getting involved in fusion, go check out this paper, because it gives you a really nice framework for understanding how all the different engineering constraints actually bound the space of what you can do and what do you have to do to actually make the system work. He doesn't. He says, I mean, there's a metric of, okay, this is this much power coming out, and ask your edge colleagues to figure out how you're going to handle it without. Yeah. Yes. Yeah. So I started from that, but yeah, I mean that's one of the things to think about, and so I did try to adapt some from there. There's more we can do, and I'm not also. I can talk about it later, but we do this type of work called a step workflow manager, but this is effectively just a set of Python tools that enables us to couple different codes together. So what assumed for this study, the goal is we want to find something that both oppose our steady state scenarios that produce this much electric power in a 4 meter 8 Tesla device. I'm just going to assume we only have simple RF sources, so they drive some key electrons and drive current, but basically assume no neutral beam. So there's no torque, there's no direct feeding into ions, there's no core fueling. Try to constrain ourselves by lowering probability of disruptions by targeting having a high Q95 and high but finite pedestal density. This is physics we can get into, but this is essentially constraining your current in the system, depending again on which coast of the US you're on versus which coast of the Atlantic you're on. Which of these is aggressive or not is a holy war matter. But then a little bit also to get at what Pat's point is, we're going to assume we have a constant Z effective of 2. And so we have this mostly deuterium and tritium, we have some helium ash, but we assume there's some trace argon in the plasma as well as trace tungsten, because you're assuming you're going to inject argon or krypton or something out into the edge to radiate power away. And so one of the metrics you look at is what's, are you staying above the LH threshold, but not much above? And then at least gives you something to think about. So the answer, after the whole other talk here, but the answer is basically yes, you can come up with nominal scenarios that do this. I'm not going to go through too much, but basically through the rest of the talk, there'll be a blue and a red one. The blue is an inductive scenario. The red is a steady state one. There's physics parameters here. In this talk, it's not that important. But I'll call these, we always need more acronyms in fusion. We can't do anything without creating new acronyms. I just call these UCAR for unoptimized compact inductive reactor, unoptimized compact advanced reactor. This can also be, I don't know if UCSD wants me to associate the UC logo with these or not, but something. So anyway, they're both here. There's profiles. The answer is this all nominally holds together. But even at this relatively high safety factor, you're still looking at something between 12 and 16 megaamps in an 8 Tesla device. So you really hope that doesn't disrupt, because that's a lot of torque on your coils. Oops. So just as an example, just kind of what does just pressure look like in these systems? This is our inductive one. This is the advanced one. And as far as the transfer goes, the main thing you can see here in this advanced steady state one is the pressure all kind of moves out to the outside, and that's a function of the beta, at a higher normalized pressure and a higher safety factor. And this outward push called the Shafanov shift is actually quite essential for the performance of the reactor, because that shift, what happens is it sort of squeezes the turbulence and it stabilizes the turbulence on the outward side. And so that shift of the flux surfaces is just kind of essential to actually get the sustained increased performance you need to keep the whole thing working together. And one of the tricks and challenges for advanced reactors, how do you convincingly generate that kind of shift if you don't have access to core fueling and torque, which are the main ways we do it now? So if you can only tailor your current profile at very expensive cost because of both recirculating power and just dollar cost a lot to RF sources. Okay, let's skip that. So anyway, trying to get back now to where hopefully the actual idea of the talk was. What I just getting to what I mentioned in the beginning, that the key commonality that was actually kind of surprising to me was that even though the heating is predominantly to the electrons, all the auxiliary heating, most of the fusion heating is to the electrons, both these systems have 50% or more of the power actually going out through the ions. And that's kind of shown here. So the green curves is how much is the net power flow through the ions. Blue is the electrons. So you can see here for the inductive case, it's quite heavily going out through the ions. It's also radiating quite a bit of power, and that's what's kind of cooling, taking a bunch of that power out from the electrons, as well as the exchange term. It's not quite as pronounced in the AP one. Again, core, there's a bunch of off-axis heating that gives you this bump, but still, for something that has that much electron heating, to be that close is quite non-trivial. Yeah, so this is the P exchange is how much energy is going from the electrons into the ions. Yeah. And so this is just another way of plotting that. So just kind of here what I'm plotting on the left, these dashed lines is what fraction of the alphas in size and radius are heating the electrons, what fraction is heating the ions. This is sort of where this kind of two-thirds, one-third ratio comes from. And then this is the ratio of the fluxes of the flows. So how much power is going through the ions versus relative to how much of the electrons. So it's about 1 for the AP case, and it's above 1 and going off towards infinity. Yeah.
You're almost less. You have no. How do you get that?
So that's coming just from the collisional exchange. But it's, and so what that, so I'll come to that in a second. But basically what that says is that it becomes a requirement on what your energy confinement time is. Because let me come to that slide if I don't answer it, ask me again. So what other interesting thing is, okay, these are my two scenarios I looked at, but also I find the exact same thing if I look at either baseline scenario or if I look at Spark, which is a small tokamak that's designed to be DT that's a private company spun off from LITs. But they have very similar kinds of things. So this is not something that's specific just to these two cases I've looked at. And so, just to give you a kind of some sense, this is the relative size of a couple of different tokamaks here in Europe. And, this is just then, kind of a comparison where, the reactors I'm talking about are here, these are Spark. So this is, an ASIC size thing, a jet size thing, heater size. It's going to be, I think, true for a demo as well, that, for a whole range of different sizes, this is a fairly robust conclusion, I think. So just kind of coming towards, why do I think this happens? The general picture is that, you have mostly your alpha heating goes into the electrons. It's going to drive TE bigger than TI. That then leads some exchange even back to the ions. So now I have power that's going to be flowing through both of those channels. Gets moved out by transport out to the edge. That's going out through the ions and electrons. And one thing I don't have time to really talk about here, but this I think this would be a good thing for students to guys. As you get out towards the edge region, radiation becomes more important, and especially once you cross the last closed flux surface, the parallel heat flow down to the diverter is going to, both of those work to rapidly cool off the electrons and pull the electron temperature down. So there's going to be some point here, at least in this kind of simple picture, where I go from TE bigger than TI, kind of this strong transport. Now I'm going to actually go to ions going to be hotter than the electrons. I'm going to have energy going back out of the ions into the electrons. So, where that transition happens, what physics sets it, I think I don't have a good sense other than this qualitative thing, but that I think would be an interesting thing to know and think about as we go ahead, because that certainly is going to affect things like the heat flux to the diverter.
Another question is how do you maintain the H node in this state? And in particular, if you drop out of H node, how do you get back in? Maybe there's a pragmatic question.
I would say you probably either lower your density or turn up your heating.
Yeah.
I mean, in some sense, I think this is good because insofar as this is putting a lot of power into the ions,
That's
that actually
good,
helps.
but then that last step. Is
Right.
what is
And so this was what I was going to actually ask about is, when we talk about the power threshold, do we care about the power going into the top of the pedestal, or do we care about the power going through the separatrix?
I mean, this is actually especially in higher field.
Yeah. Yep. Yeah.
So that's something that the other thing is you have pretty high currents. So it's complex spark, like spark.
I don't recall offhand. I'd have to. It does. I mean, so I mean, this is I don't like in mega amps. I don't recall the Spark one, but it's aiming very much like the Q95 of 3. So it's more of an either baseline like much lower Q95. So that relative sense it has more current. Yeah. Well, that's yeah. I mean, this is sort of one of the games you have to play in this. Is we know sort of empirically and for physics reasons that as you increase the current that goes through your tokamak, that helps the confinement and until it disrupts. So I tend to not think of a plasma that you know is going to disrupt as being well confined, but also if all the heat leaks out, it's not well confined either. So where that optimal place is between those two limits is. So yeah, so I think I need to wrap up. So I can talk more about this, but the only thing I wanted to kind of comment then is just at the last point, which is if you think to the extent you take that this picture is true, you can basically use your knowledge of the different instabilities and the cross phases that come with them to make conclusions about the transport. And so this is basically coming from a paper and some work that Mike Kostermuther and people at Texas have done, where basically just looking at the different instabilities have just characteristic cross phases that's just related to their underlying physics. And so, you can kind of go through your list of what your different transport mechanisms are. If you have a bunch of ion energy, you have to exhaust as well as some electron. And so basically I know the ion inclusion is too small to really make the neoplastic work. The microcarrier modes, the electron temperature gradient modes can't drive any meaningful ITG. I could have kinetic diluting modes or MHD-like ones, but those are often going to be at higher beta. They'll also drive a particle outflow. And so if I need any kind of density peaking without fueling, you can't really have those be at least regulated. You may have certain regions of them, but you can't really have them dominated. And so at the end of the day, that just leaves ion temperature gradient and maybe some trapped electron modes as only instabilities that can drive the kind of transport you need for this kind of generic scenario to hold and come together. So final slide, just thoughts, pros and cons here. ITG is actually our most well-studied mode. This is the one that we've kind of seen most. It's, we've always worried about getting the ions hot enough. That's what this comes down to at the end of the day. So, if anything, we're going to have confidence in, to the extent we should have confidence in anything, it should be producing ITG. We do have expectations that ITG and trapped electron modes should increase main ion peaking as we go to lower collisionality. This comes from some nice work by Brian Grierson. Also expect lower core high Z impurity accumulation. The two cons are if you go to higher beta, higher electromagnetic effects, that can actually weaken your pinch. So you fight something there. If you try to optimize beta, that's good for confinement, but it may take away the pinch you need. And you could also get into this way if you start peaking too much, have not efficient enough, you'll just run into a global beta. So thank you for letting me ramble on far too long. I have more to talk about if anyone wants to hear, but let's stop there and let TS get on something else.
What you want to do? something that we use. Extrapolation of the nets, but what you can do is you have several machines on the one of the all different configurations, and what you try to teach a model and design the very different things. Let's say the principle that you design is the relationship or the type of work.
I mean, not me explicitly, but it's sort of the broader range of people. I mean, people are using TGLF and this kind of thing to study everything from D3D and ASDEX, MSTX up to EATR and CFATR and demo. And so, I mean, I haven't done say for the JET results, but I'm fairly sure that they haven't been done. And I know actual modeling like this is actually fairly important for helping design the DT campaigns and what targets they want to do for things like different scenarios. So it's being used there. And I think part of that comes, something I didn't maybe emphasize, is the way TGLF is formulated. It's formulated in terms of dimensionless parameters. So there's nowhere in there does the current or the field appear. It's, the safety factor, it's, normalized scale lengths and things like that. And so I think some of the hope is by formulating that way, that gives you some ability to do things faster. And as far as I know, I don't know anyone that's done an actual real neural net directly, say, on experimental data in terms of the dimensional parameters. What we have done is things like, as you do lots and lots of TGLF calls, you build up a big database, and so you can fit a neural net to the TGLF results to get something even faster for real-time control or something. But that's still kind of relying on how well the TGLF itself worked in the beginning. But there's certainly a priori, there's no reason you couldn't do that. It's just getting the data, to right now, no, in the sense that we don't necessarily have a good model for it. And so you could fit a neural net empirically to, okay, what are the scale lengths and stuff there in the data? But sort of as what Guillaume was just asking, that would all be kind of at, we don't necessarily know what the right dimensionless parameters are to do. So you could do something if you wanted to say, okay, I've done this bunch of experiments on D3D or JET or something, I want to design another one. But for extrapolating that neural net to another machine, I don't know that there's enough confidence to really do that yet. But that's.
Up here, and